be protected. In a substation, the windings that are under the oil inside the transformer are absolutely the primary target for surge protection. Because this is called non-restoring insulation or non-self-restoring insulation, the industry spends a great deal of money putting arresters on all around transformers to make sure that the voltages never get too high. So in the substation and outside the substation, the primary purpose of surge protection is to keep the insulators from flashing over. And I'll show you in a couple slides what I'm talking about. Before we get to those animated slides, though, just a few definitions. We have two kinds of insulation. One is called self-restoring insulation, and that's usually an insulator that if it flashes over, then after the flashover and after a breaker operates, it'll self-restore and go back into service by itself. That's self-restoring insulation, and most of the insulation in a power system is that way. However, the non-self-restoring insulation, where if it fails on the inside, it's over. It's done. There's no restoring it. It needs to be fixed, taken down out of the system and fixed. So that's why we focus on this insulation, because we never want to have to get in there and fix the power system on the inside. Insulators have a couple of important characteristics that I want to talk about. One is that they will always flash over at some voltage level. If this insulators are usually rated by the AC voltage that they will hold off, but they're also rated by the impulse voltage that'll hold off. So an arrestor that, an insulator that is used on, say, a 33 kV system AC, it will often have a 200 kV withstand voltage. And this is called the BIL, or the basic lightning impulse insulation level. In IEEE terms, it's called U90, I believe. In the IEEE terms, it's BIL. So in order to apply arresters and use them properly, it's important to know what you're trying to protect. So if you have you're trying to protect a 33 kV insulator from flashing over, you need to put arresters in there that'll keep the voltage below 200 kV. So our whole business is putting arresters in certain locations to keep the insulation from reaching its flashover limit. That's for lightning, and there's also a switching characteristic, meaning that if a surge coming down the line is very slow and very long, is generated by a circuit breaker or something like that, not caused by lightning, it also has a withstand voltage, and that's called its BSL. And then there's power frequency withstand of each one too. So each insulator has a lightning withstand rating, switching withstand rating, and a power frequency withstand rating. And in order to apply arresters, you need to know what all these different levels are. Another term that's used quite often for self-restoring insulation is CFO, the critical flashover voltage. And that's used when you do a lightning study or a power system study. You usually need to know what the CFO is, and it's called U50 in IEC terms. So here's just a graphic that kind of shows the different types of surges that an insulator will see. And so this would be a slow switching surge. It has a very slow front on the surge, say 100 microseconds. Well, slow is relevant. It's fast. It's really a short time, but in the world of surges, it's very slow. Then there's a lightning surge that has a very fast rise on the voltage of say 1 microsecond or half a microsecond. And then the fastest surges that we deal with usually are flashovers of insulators that then are transmitted down the line and enter the transformer from a very flashover, and they're very, 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 very fast, even though it's a negative surge. So that's the kind of the scoop on insulators. I have a couple of animations here that can should give you a little bit better idea of what happens when lightning strikes a line. In this case, we have a power system line that's just unprotected. There's no shield above it, and lightning comes along and can strike the line. And when it strikes the line somewhere on the line, there's no telling where it's going to strike. It doesn't prefer one point over the other. It sets up a voltage on this line. So lightning is actually a current source. So we usually measure lightning and how much current it sends into the system. So say it's a 1,000 amps, which is a very low lightning surge, and it's pushing into a resistance or an impedance of say 100 ohms. You can see now voltage is I times E, so it's 100,000 right there. You're going to have 100,000. So it's going to be this is going to be 100 kV at that's a very, very low surge. Typically this is more like 20,000. So that's going to be that's going to be 1 million volts. It goes from 100 kV to a million volts. So now imagine a million volts coming down the line, and the insulator has a CFO of say 500 kV. Guess what's going to happen? It comes down the line, it gets to this insulator, and boom, you have a flashover. Now this flashover is quick and fast. Its life cycle is 20 to 100 microseconds. So it's there and then it's gone. And before it goes, though, it grows this ionized gas envelope around the insulator. So now we have a gas envelope that's very high, very low conductivity, and we have the power system here, and we have ground potential here. And when this AC voltage is there, which is there all the time, now we have the flashover because this is a low impedance through here, and now the AC flashes over, and it flashes over and stays flashed over until a breaker operates. So at some point, the power system senses a fault. The current is flowing over and down to earth, so it senses this ground fault, and very, very fast systems, it can sense it, say, in a half a cycle. Most of the time it takes multiple cycles to sense it, and then the breaker opens up, and when it opens, it then gets rid of the arc. There's no more voltage, and so there's no voltage on the system for a moment, maybe 4 or 5 or 10 cycles. Now the voltage comes back, and when it comes back, there's no short circuit anymore. So that's the whole sequence of what happens when lightning strikes a line. And this has nothing to do with arresters per se, but what we would like to do oftentimes is make sure that never happens, that we never have this sequence. So our goal is to reduce the number of outages, because now we just experienced an outage of it's called a momentary outage, but it's to the eye, it's a blink. Oftentimes you'll see during a thunderstorm, there'll just be a blink of the lights. That blink meant that lightning struck the line somewhere and caused a breaker to operate, and then the breaker brought the lights back on. But it's all done so fast, you really don't see it. Now, electronic gear sees it. Computers and other types of electrical equipment in industries can see that momentary, and that's what makes it difficult. So we try to avoid that. Let's discard those. And now there's another version of this. It's very similar, but in this case here we have a shield over the power system. So this is a typical transmission line, and the transmission line is just a bit different. Let's do the sequence. In this sequence here, lightning strikes the line, and then it travels down the line. It travels down the shield, and it keeps traveling on the shield. But at every pole, there's this down ground connected to Earth, so the current starts to flow down the pole. But remember, now this has an impedance. There's certain impedance in a line, and there's a certain ground impedance down at the bottom of the pole. So it can develop some very high voltages at the base of these insulators as the surge travels down the line. And the voltage at the base of the insulator can actually can get higher than the voltage on the phase. So when the voltage reaches the flashover level and it's higher than the voltage on the phase, we have a flashover to the phase. So this is kind of a backwards flash. That's why it's called back flashover. The surge hits the shield, produces a voltage at the base of the insulator, flashes over to the system, and now the lightning has started the event, and there's again, we have, it's over and done in 100 microseconds, but we have a gas envelope around the insulator, and now the AC kicks back in from the other direction, and now the breaker has to operate, and we have an outage on the transmission line. And when you have an outage on a transmission line, it doesn't affect one or two people. It usually affects 1 million or 500,000 or 250,000, depending on how big the transmission line is. So we try, one of the ways of protecting power systems is to put an arrestor in parallel with these insulators to keep these insulators from flashing over when lightning strikes the system. So that is the sequence of events when there's a shield on the transmission system. So I haven't mentioned this before, but you can see in this video, on this slide here, this transmission line has insulators here. It has the phase conductors, usually 3 of them, but it has these 2 fine wires on the top that go from pole to pole, and this is called a shield wire. It's a lightning interceptor. If the shield is working properly and designed properly, the surge will never get to the phase conductors. We design the systems as, so that we have very few times, maybe once in 20 years or once in 100 years, the surge can get around and get to the phase conductor. It never gets through the shield into the substation. We don't even take that into account. The shields are very effective. However, they help get the surge. The shield wires carry the surge, and we know from the last slide that some of that surge goes down, but sometimes, oops, going back. Let's open this up. Sometimes, as I showed a second ago, lightning will strike the system, and then we'll have a backflash on the insulator. And when we have a backflash on the insulator, now the surge that was also going down the shield wire is now going down the phase conductor. And that goes right down the phase conductor, right into the substation. And when it gets into the substation, if we don't have arrestors right here, we have a dead transformer. So this is how lightning gets into a substation. It never gets in by a surge from the top or right through the top. It only gets in from a backflash, either a backflash or a direct flash to these phase conductors, and then they take it into the power system. Okay, so those are the 3 kind of events that we try to take care of in power system protection. We protect the transformers, we protect the insulators, we protect other equipment in the substation from flashing over the insulators. The goal is to avoid this flashover. And the way we do that is with arrestors. So let me talk about, not the arrestors at the moment, but let's talk about the different types of surges that actually come. There's really 2 kinds. One is lightning and one is a switching surge. And they're quite different. One comes from the outside of the power system and one is generated inside the power system. So first off, this is a cloud. This is something I'm sure every one of you have seen. A thunder cloud, and we have lightning striking the earth, in rapid succession. When a storm travels through an area, you hear bang, 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 tremendous amount of lightning. And this is a cumulus nimbus cloud. And it's quite odd how it all happens, but the bottom of the cloud gets charged negatively, and it has a much more negative charge than the Earth, and that's why you get all the discharges between the cloud and the ground. And these are the ones that we deal with most of the time. There is occasional surge, say at 10% of the time, maybe. We get clouds, we get surges from the top of the cloud, and these are usually the high current curves, high current surges. So this is the kind of thing that causes most of the lightning that we deal with. Believe it or not, even in warm India, you have a lot of snow and a lot of ice, and it's up in the clouds though. As you sit down here on a hot day, up in the clouds, we have, you know, minus 25 C temperatures, and it's that temperature difference that generates these little ice grapples, and the ice grapples are the ones that transfer the electrons to different points in the cloud that give it a charge. So it's a whole sequence of ice and air currents and temperatures that generate the lightning from a lightning strike. So you can see here that lightning is not everywhere. There are many different kinds of maps that show the lightning level. We measure the lightning level in terms of ground flash density, or GFD. And so people who live in areas where there's a lot of lightning and they spend a lot more money on surge protection. They spend a lot more money on arresters in general, and other methods, a lot more money in their protection budgets. You can see that India has some very hot spots. This might not be India over here, but it's you know, much more lightning in India than there is in Europe. And notice that the farther north you go, the less lightning there is. In the U.S., we have quite an array of lightning, from Florida, where it's the highest lightning, and on the coast of California, there's almost no lightning. So it's and up in Canada, it goes from a lot to very little. So even in one area, you might have a lot of lightning on one side of a state or an area, and you'll have little lightning on the other, depending on on the geography. A couple important things about lightning that in surge protection we have to take into consideration, and that is it's very seldom is lightning a one-shot deal. It's usually a multiple shot. I know when I grew up, there was always this tale about lightning never strikes the same place twice, but in fact it is a tale, because lightning almost always strikes the same place twice. There just happens to be just a small amount of time between the strikes, say 100 milliseconds, which is a tenth of a second. So you might see a surge if you've ever been out in a lightning storm and you've noticed a flicker to the lightning, that flicker is this, that your vision can sometimes sense the different strokes, and you are able to see it just as in the form of a flicker. The other important thing is that typical peak current, the average peak current of a lightning stroke is 30,000 amps. So when we do a lightning study, we at a minimum we test it to see what happens to the power system when 30,000 amps of current strikes the system. Usually we go much higher than that. You can also see that the time to crest is 5 microseconds. For the second stroke, they're a little bit faster rise time. So these are numbers that you would need to when you're trying to do some surge protection of power systems. Another important aspect of lightning is that it doesn't always hit the lines directly. It might hit 100 meters or 200 meters away to the left or the right. And when it does that, it does put a surge on the system, but luckily the surge is much lower, and the farther away you get, the lower that surge is. So this is called an indirect strike as opposed to a direct strike, which we were talking about earlier. The other thing I didn't mention here is something called traveling waves. I demonstrated, but we didn't actually talk about it. When lighting hits a line and generates a voltage surge or voltage surge here, that surge actually travels down the line at the speed of light, very close to the speed of light. Whether it's a shield wire, or whether it's a big phase conductor, it travels close to the speed of light. And if there is no shield on a system, this surge of 1,000,000 volts will flash over these insulators. So it's this traveling wave that it causes us a problem. Well, it's part of the process that causes a problem. First, you have a strike, and then it travels in both directions. And if there was on this distribution line, if there was a transformer here, of course, we would have an arrestor, and you probably wouldn't have this flashover. It would just have a diverted to ground. This one over here might still flash over, but not where the arrestor is. For example, so here's 3 arrestors on. These arrestors are here for line protection. In this case, the user or the owner of this line didn't want any flashover on his system, so he installed arrestors even without equipment there. And what happens is the surge comes down the line, it gets to the arrestors, and the arrestors clamp it. And the clamped surge continues on. Some of the current surge goes to ground, but there's no flashover, even though there was a direct strike to the line. There's one other surge that's caused by breakers. It's called a switching surge. And the switching surge is quite different than the lightning surge. One is that it's a very low frequency, where a lightning surge is just a very small blip on the line, say 40, 50, or 100 microseconds. A switching surge can last for cycles, and that's because the breaker contacts inside of a breaker come closed, and as they come closed, sometimes they spark over or arc over between the contacts. We try to make this as fast as we can so it reduces the surge, but almost always there's some sort of surge depending on where you close the switch, whether you close it at peak or at 0 volts. There's some kind of surge on the system. And this surge then is high enough that can cause, in some cases, can cause the insulators to flash over. So we spend a lot of time and effort to make sure that switching surges also do not cause flashover in systems. Okay, now to the arrestor, and a little bit about what's inside the arrestor. Again, these are the different types of arrestors. This would be a station class arrestor, these here, and a distribution arrestor. And there are some low voltage lightning arrestors that do get applied below 1,000 volts, but and the ones that are designed to handle high currents are also called arrestors. Similar to the slide earlier on the different types of arrestors, the one I didn't show you before is this is called a transmission line arrestor, and the reason is it's mounted in parallel with the insulators on a transmission line. And then these are the distribution arrestors, and then these are station arrestors. So these are what they look like today. Every arrestor has a classification, whether it's classified by IEEE standards or classified by IEEE standards. Every arrestor manufactured today has to be tested to some minimum levels. Most of the time, a country will adopt the international standards, but oftentimes they make them a little bit tougher. For instance, I'm not sure what the India standards are, but India has its own set of standards for surge arrestors, but they're oftentimes very much in line with the IEC standards. Actually, the only country that really uses IEEE standards is the U.S. Most of the world tests and specifies arrestors per the IEC standard. And as of the last 10 years, these two standards have come together. So if you buy a IEC specified arrestor, it's going to really be specified the same way for IEEE. We all have tables that tell you what the currents are, what the ratings are. The U sub C or the MCOV level is what an arrestor is usually rated by. We'll talk a little bit more about that in a second. Inside the arrestor, as I was showing you earlier, this is a rubber housing. This is a station class arrestor. There's a rubber housing on the outside. Quite often you'll see this made out of porcelain still. But on the inside, we have these metal oxide varistors, same as we saw in that little presentation on the distribution arrestor at the start. There's usually a spring to keep things under pressure, and there's top terminal and bottom terminal to make sure that it can stand by itself, or it can support a line, or if it does fail, it doesn't blow apart. So this is what a polymer house station class arrestor looks like. Here's what the distribution arrestor looks like. It has the MOV blocks on the inside, rubber housing on the outside, the top terminal, a bottom terminal, which is a little bit different than a station arrestor. I'll tell you about that in a second. And then usually has a plastic hanger to hold it in place. This section on the bottom of the surge arrestor, of a distribution surge arrestor, has a ground lead disconnector built into it. There's different forms of it, but it looks differently in some places. But it's usually it's a disconnector that's used to disconnect the arrestor only one time at the end of life. And I'll talk about that again in a second. This is what they really look like up close outside. All of these were in service on a transformer or on a line somewhere. This was in a substation, I think, on a power transformer. These are all 30 years old, so you can see they get a little bit funny colored, the polymer housings. And here's the ground lead disconnector on this one. Sometimes the material that was made back in the 90s, some 40 years ago, isn't quite as good as the ones made today, but most of the polymer material today is very, very good. We'll skip that one because, well, not really. All insulators, whether it's an arrestor or whether it's just a plain insulator, has this thing called creepage distance. And if you draw a line over the surface, over all the sheds or skirts, if you draw a line over here, this distance is much longer than a straight line. And this creepage distance is used primarily to keep this insulator from flashing over when it's wet. So when an insulator or the insulation on the outside of a arrestor is very, very wet, or contaminated and wet, say contaminated by salt water, so a conductive contamination, it can flash over. If we didn't have the sheds, it would be a short distance and it would flash over. So we elongate the surface on the outside by putting these sheds on. So these are necessary for outside arrestors, but not necessary for inside arrestors. When I say inside arrestors are often used in an indoor substation or industrial substation or in a train station, that kind of thing. You don't need the sheds if they're protected from the weather. Back to the ground lead disconnector on the bottom. Most distribution arrestors today have this device on the bottom, and the purpose is that if this arrestor should fail, for whatever reason, an animal got across it or moisture got inside, there are a couple different reasons why arrestors can fail. Maybe lightning was too high. That doesn't happen too often, but it can happen. During that last event, this disconnector opens and operates. It actually has black powder on the inside, and it blasts the whole thing apart, and the line swings down. So the line comes down, and it disconnects the arrestor from the power system. So this is a way of holding the reliability of a distribution system up. If you didn't have the disconnector, it would stay connected, and you'd have a short to ground, and the whole distribution line would shut down. This way, it automatically disconnects, and then the power can come back on, and it improves the reliability level of a distribution line. You also may have seen at the top of some of these taller arrestors these big metal rings. And these are what we call grading rings, and they are there to generate a different stray capacitance to the line. This is called the grading. What it does is it equalizes the voltage along the outside of the arrestor and on the inside of the arrestor. And without it, it might overheat. So we put grading rings on arrestors. And it's really a complex topic, but I just wanted to let you know that it does exist and what they're for. This is the characteristic curve of an arrestor. And it's really important. If you're an arrestor designer, it's not so important to the user. And all arrestors have it. And if you're ever going to do a lightning study, though, or using ATP or EMTP or any kind of transient software, you would have to know this characteristic curve. I'm not going to go into it today, but it is an important curve. It shows you at what voltage and current you'll have. So if the lightning strikes and it has 50,000 amps, you'll know that the voltage across the arrestor is going to be at some level. So it tells you very precisely for different current levels what the voltage levels will be. So it's like any characteristic curve of any semiconductor. Let's move on. One of the things that you'll run into if you ever start using arrestors is you'll find these tables, and they can get kind of confusing sometimes. And this, what it says is that at 10,000 amps, this is what the voltage will be on this arrestor. So if you are trying to determine whether to buy an arrestor from ABB versus one from Siemens versus one from Hitachi, you can then compare these numbers from the data sheets that all manufacturers supply. This is a real micrograph using a scanning electron microscope. I talked about earlier about the grains inside of a MOV block. This is the diameter of a hair, a very fine human hair. And you can see in the very clearly, you can see the different grains of zinc oxide. This is at, what's this magnification? This is 5,000x here. That's actually a little bit more than that, but you can see the junctions between the grains. You can see these junctions, and you see the grain itself. So understanding this is pretty important if you're working with the chemistry of a zinc oxide arrestor. It's nothing to do with application. So here for the next few minutes, then I want to talk about the different types of application of arrestors. In a substation, there's about 3 or 4 places where you'll see arrestors, and each location is protecting certain things. For instance, we call this the line entrance to a substation, and sometimes you'll see arrestors either up here or high on the tower or down low, and the real purpose for these arrestors is to protect the bushing on the breaker. You don't usually see arrestors on the line entrance if there is no breaker. So this arrestor protects these bushings, and we can't go into the details of that, but that's its purpose. The arrestors that you see on the transformer are all about protecting the windings on the inside. Yes, they do protect the bushings here, but the real purpose is the windings. So in this case, these arrestors here are protecting the primary windings, and these arrestors are protecting the secondary windings. So these arrestors are ones that are used for protecting the transformer. This one has a little bit of effect on the transformer protection, but not very much. At the exit of a substation, you'll see arrestors, all kinds of arrestors. In this case here, it's an underground feed out to some residential area maybe, or some industrial area. And these arrestors here are protecting this cable. The purpose of arrestors on the riser pole are protecting cable, not really protecting the transformer at all or the breaker or anything. It's really about protecting this cable. Now they will have some effect on this secondary breaker also. So those are the applications. Oops, this is the same slide, just differently. Here's some real world images of what it might look like. This is a 69 kV transmission line, and there's 3 arrestors up here, one on each phase, and there's no shield wire on this system. So this is a unshielded 69 kV system, and arrestors are put on every single pole all the way through the whole system. They have, in the city of Lakeland, they have about 200 poles, so there's arrestors on 200 poles. How High voltage cable is another area where there's a lot of protection needed. And when I say high voltage, say 245 kV or 115 kV, this cable needs to be protected. Both the sheath and the center conductor. This is an actual pole showing the arrestor is tied all the way over here to this phase conductor, and that's protecting the phase conductor. And then this is a sheath voltage limiter here that's actually protecting the sheath on this one. The sheath voltage limiter is a kind of an uncommon type of arrestor, but it's used in high voltage cable protection. Down underground, there's some vaults sometimes, and you'll see sheath voltage limiters also underground. Here's another transmission line arrestor that's protecting this insulator from ever flashing over. So the purpose here is never to have a flash over on that insulator. This arrestor is protecting the inside of the cable, and this is the sheath voltage limiter protecting the sheath. Another common location for arrestors is in wind farms, or any substation actually. In wind farms, there's usually many underground cables coming in, and they come in and come up, and they come up to breakers. And each breaker then has a set of arrestors on them, and it gets very complex. Then there's arrestors back here. I don't see the transformer. Transformers back behind here. Pardon me. So this is what the substation entrance would look like in a wind farm, and there's many arrestors inside these for protection. I mentioned the underground circuit a moment ago. Excuse me a second, I need a drink. I mentioned underground circuits. We call these riser poles. Sometimes they're called terminal poles. The arrestors are put here for protecting the cable, and they do give a little protection to the transformer at the other end too. But oftentimes arrestors are put right inside the transformers on the underground transformer. There's usually one arrestor for each phase. These are usually like the cream of the crop in arrestors because it's very hard to protect underground cables because of voltage doubling in the circuit. This is what it looks like. This is a riser pole arrestor protecting underground cable. This is an example where the underground cable isn't protected quite so well because the arrestor is way up here. Usually when we're trying to protect cable, we try to keep the arrestor as close as possible to the top of the cable. In general, that's a rule of thumb when you're doing surge protection. Always trying to keep the arrestors as close as possible to the power system that you're protecting, or to the piece of equipment you're protecting. Here's a high voltage substation in Florida. These are quite compact. When you get into urban areas, things are really tight. It's very confusing as to what wire goes where. But the solution to this is called GIS. And what we're seeing pop up around the world are gas insulated substations. And a gas insulated substation is very small in size, because instead of using air as the insulation, it uses SF6, and it's all enclosed in metal housings, and it can be used for in urban areas. Here's some old arrestors that are on that system. The reason for polymer arrestors is that they don't blow up. Porcelain arrestors, if they should fail, they have a tendency of blowing up, and they can cause damage on other equipment that's more higher in value. So the reason polymer housed arrestors have become so popular in the past 20 years is for safety. This is a very common distribution system where we have a three-phase transformer, and we have arrestors that are protecting each phase. And then we have fuses that are protecting for overcurrent protection, but arrestors are meant for the underground, the overvoltage protection only. Here's kind of an old arrestor, old and new together. We have an arrestor that has a ground lead disconnector and then we'll be housing, and then an external gap on it. And this is just kind of it's done along the coast where there's a lot of contamination. So that's just about it. On protection, on distribution lines, oftentimes we see arresters applied just to keep these insulators from flashing over. At the end of lines, sometimes on one side of the circuit. So line protection is more popular in the higher lighting areas than in lower lighting areas. And I think that's it. Yes. So it's been a pleasure talking to you, and I'm open for questions, as many as you'd like to ask.
Thank you, sir. It was indeed a great session. This would be a great asset for all of us. Now, we will have a question and answer session. You can unmute yourself and ask your queries. You can also post them in the chat box. So we have a question coming up.
Okay.
Where do surge powers come from apart from lightning?
Say it again, just a little slower for me.
So where do surge powers come from apart from lightning?
The only place surges come from apart from lightning would be from breakers. Well, not the only. So let me give you a few examples. The breaker, when a breaker operates, it'll generate a switching surge. If one line, a higher voltage line, falls on a lower voltage line, that generates a very high surge on a system. So it's where two systems of different voltage touch each other. Sometimes a car will hit a pole and the line will drop to the ground, and you can get a surge from that, from a line drop. That's about it.
Thank you, sir. We have another question from Rashi. Is SPD still necessary even if we have good grounding?
Well, it depends on what you're trying to protect and what your goals are. So if you have good grounding and you are in a very, very low lightning area, don't put the SPD up. There's no real need to. If you're in a high lightning area, grounding will not help you. You need the surge protector. And if you're referring to a SPD as a low voltage device, which is typically the term for low voltage devices, the cost of an SPD is so low compared to the cost of replacing a piece of equipment. It's very low cost insurance.
Thank you, sir. Next is a question from Varun. Do SPD have any disadvantages?
Yes. When you put an SPD up on a system, it itself has a failure rate. It's very low, and it's getting lower and lower as the years go by. So if you're trying to improve the reliability of a system, you have to take all the probabilities of an outage, and now as soon as you add a component, you have to add another probability of failure. So there's a bit of a disadvantage there. However, I must say that the failure rate of arresters are in the part per million, and for most of the world. So if your failure rate of your arrestor is high for whatever reason, then you have to build in failure rate probability into your protection scheme.
Thank you, sir. Next question. As MOV is an arrestor, is sensitive to voltage, does it absorb any amount of lightning?
Yes, it does. It can absorb as much as 5% of the surge or the energy or the charge. Well, it doesn't absorb the charge. What it does is when it's passing the current through, the small resistance that's left when the grains don't turn into a perfect conductor, they will dissipate energy. And for some systems, that's important. Uh, if you're trying to protect a large transmission line, say a 400 kV transmission line, the amount of energy that the arrestor dissipates can become an important factor. With lightning, it's not usually an issue. It does collect some of it, but not very much.
We have another question. How dangerous could it be if the SPD doesn't function properly?
Well, again, it's very situational. If the arrestor is in a substation and if it doesn't function properly, in this case here, if it doesn't, it's usually they're supposed to stay together, not blow up. They're designed to not ever come apart. But if it malfunctions and comes apart, it can be dangerous to people if they're in the substation. It can be dangerous to the equipment and cause serious damage to the equipment. So it can be dangerous. Usually it's not, though. If it malfunctions, say if it fails inside and blows its disconnector, it really just blows the disconnector apart. The arrestor stays right there. There's no danger. So typically it's not a hazard. Sometimes on rare occasions it can be.
Next question. Which type of earthing is good for lightning arrestor?
A lightning arrestor doesn't care about earthing. It's almost not relevant. If it's in a bad earth or a good earth, it still works the same. And that seems quite counterintuitive, but arresters usually protect just as well whether there's a bad earthing or a good earthing.
Next one. Is there any warranty on surge protector?
Every manufacturer has a little bit of warranty of some sort. For instance, if an arrestor was to fail in the first year of life, the manufacturer usually will replace it. It's not the standard. There's no standard warranty of any sort. If an arrestor fails 5 years out, if one arrestor fails, they'll probably not do anything about it. If 50 arrestors failed and they could determine that it was a manufacturing problem, then they might give you some kind of warranty, but it depends on the company.
Next one. How to protect high-rise buildings from lightning?
Oh, not with arresters. That's a lightning rod. Now, the lightning protection systems that are used to protect tall buildings, are really just ground wires. And sometimes, though, when the ground wires do carry high current from the top of the building to the bottom, it does pass by the power system. And indeed, this is why it's usually good to have small voltage SPDs on your TV and the different machines that you use in a home or in a high rise.
Next, what is the difference between surge arrestor and lightning arrestor?
Nothing really. Their terms are used interchangeably quite a bit. The arresters that are mounted in a substation they deal with switching surges and lightning surges. So they really handle all kinds of surges. The arresters that are applied out on the distribution system really only deal with lightning surges. They don't really deal with switching surges. So it's more like a lightning arrestor only, where the arrestor in a substation would be for lightning surges and switching surges. And, it's really being picky to say they're different, but they're just the slightest difference. But many people use the terms completely interchangeably.
Next question. Do we need surge protection even if we connect our device to UPS?
The UPS needs surge protection. I mean, lightning will damage a UPS in a millisecond. So the so now, does your equipment on the other side, like your TVs and refrigerators, do they need it if there's a UPS? Yes, because the UPS is I don't I'm not sure. I guess it depends on if all your power goes through the UPS or if the UPS just comes on when the power goes off. So surge will still come through our UPS probably into the system. Then you would need a surge protection. Yes.
Do we have any questions left? I guess that's the end. Thank you so much, sir. It was really informative. You really helped us to clear our doubts and get a more clear picture on the topic.
Very good. And it's a pleasure talking with you. And these are good questions. And if you have any more, please don't hesitate to email me. I get questions almost every day from around the world on little things like this. So it'd be a pleasure to answer your questions.
Thank you, sir. Thank you, Jonathan, sir. This is Arun Kumar, sir. Thank you for sharing your vast knowledge on protection, sir. Thank you. Thanks a lot, sir. Definitely, we will contact you in future. We are trying to include some advanced technologies on production, especially for power system. Okay, so definitely we'll talk to you and we will try to collect the material before we frame our future curriculum, sir. Thank you for sharing your experience, and definitely we'll keep in touch you in future, sir. Thank you. Thanks a lot, sir, Jonathan.
You're very welcome. Take care. Have a nice weekend.
Thank you, sir.
Thank you, sir. Thank you. Wish you the same, sir.
Next, we have a small token of appreciation. I request Rashi to present the virtual plaque. Before leaving, I request everyone to turn on their cameras for a moment so that we can take picture of the session. Feedback form link has been shared in the chat box. I request everyone to fill it up to receive your participation certificate. Please turn on your camera for a picture. You may leave the meet now. Have a great day.